Okay, here's electrochemistry part one. We're going to learn about the basics of electrochemistry, review a little bit of redox reactions, and get into electrochemical cell potential. It's very exciting. Here we go. So oxidation reduction reactions are the ones that drive electrochemistry. And that is because when one species is oxidized and another is reduced, there's a transfer of electrons. Because electrons are moving, you can harness those electrons. And when you harness electrons and make them do work, that's electricity, right? And so in this case, we're taking solid zinc and reacting it with some sort of acid, right? And then the acid is oxidizing the zinc, right? The zinc goes from a 0 charge to a +2 charge, and the hydrogen is reduced. Hydrogen goes from a +1 charge to a 0, right? And in that process, electrons are transferred from the zinc to the hydrogen, right? And this is the crux, this is the basis of redox reactions and electrochemistry. And so this is looking at this on a more particulate level, right? You have your zinc and your hydrochloric acid, then you get zinc chloride in the solution and hydrogen gas as the bubbles, right? But when that happens, there is a transfer of electrons, and that transfer of electrons is what causes electrochemistry. And so now that you have an idea about electrochemistry, redox reactions or oxidation reduction reactions are often written as net ionic equations. And because they're written as net ionic equations, they can get kind of funky to balance. And so in order to do this, this is a method that you can use to balance oxidation reduction reactions. So the first step you're going to do is you're going to put the reduction half reaction and the oxidation half reaction, and you're going to split them up, right? That's going to be the first part of this. And so here's a reference for you. Here's all the steps that you're going to need to do in oxidation reduction reactions by this method. And so there's 7 steps here. I'm leaving this page here as a reference for you. It's not something they're going to have to do on a regular basis, but it's something that you may find useful in the future. So here's something that's my gift to you. And so what I want to do is I want to walk through this process just for fun. Okay, it's nothing that I'm going to ask you to do in the future, but part of this is important, like identifying the oxidation states and all that kind of stuff. So the first part, where you're dividing the equation into 2 half reactions. So the first half reaction is where you're taking the chromium, the dichromate ion, and it's becoming chromium 3. So the dichromate is going from, let's see, 7 times -2 is -14. So it's -2 overall. So you have +12 left over. So this is +6 here. So it's going from +6 to +3. So that's going to be 3 electrons each, right? And then Cl minus is going to Cl no charge. And so that's going to be 1 electron each, right? And so the half reaction equation is the Cr2O7 goes to the 2 Cr3 pluses, right? And then you add hydrogens on the left-hand side to balance out, or you add waters, I'm sorry, on the right-hand side to balance out the oxygen, and then you add hydrogens on the left-hand side to balance out the hydrogens from the water, and then you have your oxidation half reaction, and you're balancing that. Then you add electrons to balance the charge, right? So you have 6 electrons on the left, right? And then 2 electrons on the right, or 2 electrons in the oxidation, I'm sorry. And so then you've got to multiply through to get the same number of electrons. And then you combine them together. And that is your final balanced equation. And you got to make sure that there's the same number of each type of atom on both sides of the equation. So, like I said, this is bonus knowledge, just so that you have it in case you want to refer to it at some point in the future. Here's the meat of what I want to get get to, though. Here's the real good stuff. Okay, here's the new stuff. Okay, we're talking about voltaic cells. So a voltaic cell, by definition, is a cell that runs spontaneously that generates a voltage. It generates electricity. And so there's two parts. Well, there's a bunch of parts, but there's two halves to your voltaic cell. There's the anode, where oxidation occurs, and then you have the cathode, where reduction occurs. And so the way I remember this is that anode starts with A and oxidation starts with O, and those are both vowels. So anode is where oxidation occurs. And then reduction takes place at the cathode because R and C, right, are both consonants. So reduction at the cathode. Okay. And so this is a beautiful diagram to illustrate all the aspects of voltaic cells. Okay, you have electrons that are flowing from the anode through your voltmeter, which measures your voltage, or to your electric source, like your light bulb or whatever, and then it goes back in here to the cathode. So your electrons go, they do the work, and then they keep going, right? Because moving electrons are allowed to, are able to do work. And then you have in the middle, you have this salt bridge, because you can't just have electrons flowing, right? Because that would build up a charge difference, right? And you can't have charge difference. So when electrons are leaving the anode is getting less negative, right? So because it's getting less negative, you have to have negative anions moving into the solution. So then that balances out. And then this side is getting more electrons flowing to it. So it is getting more negative. So you have to have positive cations flowing from what is called your salt bridge to your solution. Okay. And the salt bridge is the connection between these solutions, so the solutions can know that the other solution is there, kind of. Okay, it's actually just there to balance the ions. And once it balances the ions, the electrons can flow, because electrons won't flow unless there's charge balance. Okay, and so then this little direction shows you, this little indication here shows you the movement of the cations and the movement of the anions, and then it has the half reactions that are occurring on each side. So in the anion, you notice, or in the anode, you notice that you have zinc going to be being oxidized, right? Because oxidation occurs at the anode. And on the cathode side, you have the copper ions being reduced to copper solid at the cathode. And so on the anode side, your actual metal anode is being dissolved away, right? Because the zinc is being converted from elemental form into ionic form. And then you see on the cathode side that the copper ions in solution are being plated onto the copper cathode. So lots of stuff going on in voltaic cells. It's super exciting. But the key that I want you to remember here is that oxidation occurs at the anode and reduction occurs at the cathode, and the construction of a voltaic cell, the things that you need to have in order to have a voltaic cell. You have to have your anode compartment, you have to have your cathode compartment, you have to have your bulb connected there, and you have to have your salt bridge. Okay, and the electrons always flow from the anode to the bulb to the cathode. So the electrons go A, B, C. Look at that. That's so cool. All right, so here is standard reduction potentials. So they wanted to determine how to gauge how much electricity is being generated in any situation. And we wanted to, of course, in chemistry, make this predictable, right? So they came up with the the standard half reaction potential for a reduction half of a reaction, right? That's why it's a half reaction, because it's only the reduction half. So they decided to come up with a zero number, which was very arbitrary. But the arbitrary zero value is hydrogen being oxidized, or I'm sorry, hydrogen being reduced, because they're all reduction reactions. So they're all written as reductions. So hydrogen ions, an acid solution being reduced to hydrogen gas. Okay, they figure hydrogen's the smallest atom, so let's make that the standard. Okay, and then everything else is measured based upon that. And so the highest reduction potential means that this has the fluorine has the highest ability to be reduced, right? And this makes sense because fluorine really wants to get electrons. So fluorine gas will steal electrons and become a fluoride ion very readily. In fact, the standard reduction potential for that process is the highest on this table, right? And then if you think about, okay, well, what's the easiest to do? Well, the easiest is going to be to oxidize one of the alkali metals, right? So lithium, um, its reduction potential is negative because the things that are at the bottom of this reduction potential really don't want to be reduced. They want to be oxidized. Okay, and so this is giving you the voltage that you're going to gain from each of these processes happening. Okay, and the most energy you get would be from fluorine getting an electron, getting two electrons, right? Because there's two fluorine atoms in a fluorine molecule. And the most energy you would have to spend would be to take lithium ions and make them into solid lithium. Okay, so that's how cell potential works. And then you take these and you combine them together because you can't have just reduction happen. You have to have reduction and oxidation. And so in order for you to figure out the cell potential or the amount of energy that is available to do work from an electrochemical cell, you take the E0 of reduction from the cathode, so the reduction part, minus the E0 of reduction for the anode. And the reason why it's a minus sign, this minus sign down here indicates that it is you're doing the opposite process that is listed in your reduction table, right? So this negative sign switches the sign for you automatically, right? So you use standard reduction potentials all the time when you're calculating electromotive force or when you're calculating the cell potential. But notice that it's the cathode minus the anode or the reduction minus the oxidation because it has to switch the sign of these things because you're switching that process. Okay, and so when you're calculating cell potentials, right, you are taking the reduction minus the oxidation. So this is an illustration that shows you how it is determined what a standard reduction potential is because you use the standard hydrogen electrode as your zero. Okay, so this is a standard hydrogen electrode. It contains an acid solution, right, and hydrogen gas flowing through it at 1 atmosphere, standard hydrogen solution of 1 molar, right, and then you have some sort of non-reactive electrode in here. Typically, this is platinum. It looks a lot like copper in this illustration, but you couldn't use copper. You have to use some non-reactive metal, right, some noble metal. So that's why platinum is used as the standard. And so that's how this is how you would figure out what the reduction potential of zinc would be because you could compare that to the standard hydrogen electrode and see what happens. Okay, so here's an example calculation for how to use the cell potential equation, or the E0 of a cell is equal to the reduction minus the oxidation. So it's giving you an example problem, and it's pretty simple math, right? You have 1.1 equals the E0 reduction of the cathode minus negative 0.76. And what you can't see because my bottom screen won't go away is that it equals 1.1 at the end, right? Or 0.34, I'm sorry, is the reduction potential for copper. So your table of reduction potentials gives you the best oxidizing agent or the thing that allows oxidation to occur, which is what is most easily reduced, and then the best reducing agent. The reducing agents are the ones that are allowing that are oxidized to make to allow reduction to happen. Okay, and so that's all I'm going to do for this presentation. And then I'm going to show you, these are the book problems that I want you to work out. And for most of them, it's going to be kind of some review of oxidation numbers and redox reactions. And then you're going to do some calculations. Okay, so if you have any questions, please feel free to ask. And good luck and I'll see you next time.